chapter 7 is internal forces and shear and bending. That's half of your test. Chapter 8 is friction, new book. And let me close these guys. And so friction. And so there's basically about 5 questions. There's about 20, or a little over 20 questions, and about 5 questions per topic. Usually on shear and bending, there'll be a few more questions because some of them are conceptual. But on friction, you've got general friction problems, you've got wedge type problems, and you've got belt friction problems. And so the general problems, I give you some general notes here which you should look through. And one of the things I want to comment on this is angle of friction. You guys talk about angle of friction in class? So if you put an object on a yardstick or on a surface and you increase the angle of this guy, and at some angle it'll start to slide. And from that angle, you can actually calculate the coefficient of friction between this surface and that object. And the way it works is and Himmler talks about the angle of friction, but it's like buried in one of his example problems. It's just like, you guys don't ever read the book anymore, do you? And so, anyway, so this is a picture of an object on a slope. And so you have a free-body diagram as an mg, a normal force, and a friction. And if you tilt this guy up so it begins to slide, then you can set F is equal to mun. And so in the normal direction, the normal is equal to mg cosine theta. And then in this direction, F, if it's just on the verge of slipping, you've got F is equal to mg sine theta. And if you say, and if it's on the verge of slipping, then you can solve for mu is equal to F over n, which is mg sine theta over mg cosine theta. Well, the mg's cancel, and you get tangent of theta. And so, solve for mu. So mu is equal to tangent of theta. And so basically, so if you take any object and put an object on it, and you lift it up, and you can get an angle, and it's a way of calculating the coefficient of friction between that shape and this guy. And it's called angle of friction. And so that sometimes shows up on a test. And so just be aware of that. It's supposed to be an easy problem, but you have to know it. You have to see what's going on. So just be aware of that. Let me show you some example problems. So a classic problem that more often than not shows up on either the third exam or on a final exam, and it's basically a crate slip tip problem. And you're finished frictions. You're in center of time. Yeah. So you should have done this problem, and you probably have one in your homework. And so you basically have a crate that's shorter on this side and taller, like a refrigerator, like a filing cabinet, something that's tall and narrow. And there's usually a force P acting on the side, and then you give it a weight that's concentrated at the center, and you're typically given a coefficient of friction. The problem typically says, at what force P will this crate move? And you have to realize that what it's really saying is, you've got to check tip or slip. It won't necessarily say that or not, but you have to realize I have to check both cases. And so I do this differently than the way your book does it. I just concentrate the normal at the corner and the friction at the corner, which is the case at which it's on the verge of tipping. If it's not tipping, it's not tipping, then the bottom of this guy, I think it's following okay today.
Yeah, I think it's because we have it farther back.
Okay.
So.
Okay, that's nice. So if it's not on the verge of tipping, then you really have a distributed load underneath that object. And so if it looks like this, and you got a small value of P or no P at all, there really is a distributed load here. If it doesn't have feet, there's just a flat bottom, then there's a distributed load across the bottom, and then there's a normal that's typically off center, which is the resultant of this distributed load. And as you push on it harder and harder and harder, this guy kind of starts tipping just a little bit, and this distributed load shifts toward the right, and ultimately when it's on the verge of tipping, then this normal is at the corner. That's what's really happening. But and that's the way Hibbler works it in his example problem. And he calls this X. He calls this X or something like that. He calls it X. To me, that's way too complicated. It's way too complicated. And so just draw a simple free body diagram with the normal at the corners. This is the tipping case. And so to check the slip case, then you basically set the normal is equal to weight, which is 80 pounds. And then 80 times 23 is 24 pounds. And so P slip is 24 pounds. That's when this F reaches its limit. The tip case, you just put the normal and friction at the corner, you sum moments out at the corner, and then you have a P times 4 in this direction, minus 80 times 1.5 in this direction, and then you can solve for P tip, which is 30 pounds. And so in this particular example, the slip will happen first, and then the answer that you report is the 24. And so that's what it's asking for. What P does this guy slip? This is a very common general friction problem. Questions on that? You should be prepared for something like that. Ladder problem. So there's a variety of different ladder problems, and I've got some others that I'll show you here in a moment. And friction problems, this particular ladder problem is, the question is, will the ladder slip? It doesn't say it's slipping. It says, will it slip? Later, I'll show you another example where it basically says that the ladder is on the verge of slipping. So any friction problem, read it really carefully. If it says it's on the verge of slipping, then you can set F is equal to mu(n). But if it basically says, will this slip, then do not set F equal to mu(n). Treat F as an unknown, okay? So then you calculate F as an unknown, and then you calculate N as an unknown. And you're typically given a mu, but the reason that you're given a mu is once you calculate F, and once you calculate N, then you check. You basically say, is my F over N from my calculations, is that less than or equal to the mu given? Okay? And so this is what you have to do if the problem says, will this slip or will this move? You can't set F equal to mu(n). And that's a common error that students want to make. That they see a mu and they go, F is equal to mu(n). But read the problem carefully. Don't do that unless it says it's slipping or it's on the verge of slip, okay? Read it carefully. This particular problem, this ladder problem, it says, will it slip? And so you draw a free body diagram. And so we have a weight, which is 80 pounds. We have a 5, 12, 13 slope. Often for a ladder problem, we'll put friction as 0 on the wall, just to make the problem a little easier. So there's no friction here. It says the wall is smooth. There's a friction at A and a normal at A. And you're given a mu, but again, you're not told that it's slipping. So I have 3 unknowns. I have FA, NA, and NB. Well, I've got 3 equations of equilibrium, so I can solve for all 3 of these guys. And so if I sum moments about A right here, I get NB is equal to 6.67. If I take a vertical summation, because the wall is smooth, the only vertical forces are 80 and the NA. So NA is 80. And then if I sum forces horizontally, I get FA is equal to NB, which is 16.67. And of course, I found NB from the moment equation. So now I have my three unknowns, NB, NA, and FA. But I'm not done yet. I need to check. The F that I calculated divided by NA is 16.67 over 80, and that's 0.21, and that's less than my mu given, so my letter will not slip, okay? And so I've proven my letter will not slip. There's some practice problems, other practice problems in this folder from old exams that I put out here. And I'll zoom in on this a little bit. Here's a crate problem, crate slip tip problem. Here's basically a ladder style problem, but it basically says, find the P that will prevent this ladder from sliding down. And this is a weird problem. It's weird. It basically is the contacted B, so this is smooth, so there's no friction here. And it says the friction between the rod and the wall is 0.2. So you basically have a friction and a normal here. You only have a normal here. But again, this guy is on the verge of sliding, so you're trying to find a P that prevents it from sliding, okay? But because it tells you it's on the verge of sliding, then you can set F is equal to mu n, and then you can write equations to solve. And I guess in this case, we summed moments around B. Oh yeah, so this is 0.2 NA and this is NA, so there's really just one unknown. So if you sum moments about B, you got the moment of the weight, and then you got these two components, which you can solve for NA. And then once you get NA, then P is, if you mentally sum forces in the x direction, then P is equal to NA. But again, this is different because it tells you it's slipping, and you're applying a P to prevent that slip from happening. Questions on this? Just read the problem carefully. And again, here's another example, but this guy's different. This guy here is the minimum P to initiate movement. So now you're pushing it up the wall, and now the slipping is taking place here, the friction is taking place here, and wall is smooth. But it's basically kind of the same problem. Here's a slip and tip problem. Spool problems. So you don't have any of these in your homework, or hardly any, but these guys show up on our tests. And so this is a spool. You got a cable wrapped around the spool, and you're applying a couple here. And the problem is find the couple required for the spool to move. And so if the couple gets large enough, it's going to slip. And so basically, when you draw the free body diagram, you've got a normal here, you've got the tension here, and then you've got a friction, and then the friction is equal to mu times the normal. But because of this problem, the normal is exactly equal to the weight, and 0.25 times the mu gives you the F, and once you have the F, then that gives you T, and then you can solve for the moment. And I guess I sum moments about B is what I did, and you get the moment to cause this guy to slip. There's one other spool problem here, and this is a spool, or a cable wrapped around the spool, and you're coming upward, and you're given the wall is smooth, and this is friction here, and you're finding the force P to initiate movement of this guy. And because because movement is on the verge of happening, then you can set F is equal to mu n. The direction of F is opposite of the relative motion. And so you draw the free body diagram, and then you can solve for P from this. If you sum moments about C, then, bless you, if you sum moments around C, basically P is 9, and then F is 9. And these guys act opposite of one another. If you sum moments about C. So those are general problems, general friction problems. Friction's an inequality. Friction will vary from 0 to whatever it needs to be until it reaches its maximum it can be, which is its maximum is mu n. Friction always acts opposite of relative motion, so look carefully at the problem and look at the surface where contact is occurring. And if that guy is slipping this way, then friction opposes it. If it's slipping this way, then friction opposes it. So that's your thought process. Those are general problems. Let's look at wedge problems. So wedge problems, there's a folder on wedge problems. And I gave you some old exam wedge problems. Let's talk about self-locking. So there's often a question about self-locking. You know what a self-locking wedge is? You need to know what a self-locking wedge is. So, how many of you ever taken an axe and buried it into a log and then it got stuck and you almost can't pull it out? That's a self-locking wedge. And so a self-locking wedge is typically a wedge that's very narrow and you deeply bury it. And because of that, you can't pull it out. That's called self-locking. If you have a wedge at your sorority or your fraternity that you slide under a door, and if the wedge angle is too high, then it just pops out. It doesn't lock. But if that wedge angle is slow enough, then you kick it with your foot, it slides under the door and it stays. You like a self-locking wedge under a door so it stays where it's supposed to be. And it's super annoying when the wedge keeps popping out. That's self-locking. And that often is on the test as a conceptual question. So how do you check self-locking? So there's really, so in every case, so remember with wedge problems, you have problems where you're pushing on the wedge, and that wedge is lifting something. And so if you're pushing on the wedge, and it's the lift, what I call the lifting case. So if you're pushing on the wedge, you've got a theta here, you're pushing on the wedge, there's a normal here, there's a normal here, and the friction forces oppose the direction of slip. This is N, B, F, P, N, A, F. And so I've got a P here. So this is the lifting case. So I'm pushing on this wedge, I'm using this to level the machine, to level the beam, and the friction forces act opposite of the motion of the wedge. That's the lifting case. The lowering case, sometimes you might use a wedge to lower something. And so you got basically the same wedge, you have a theta, but now you turn P around. And there still is a normal B, there still is a normal A. But now you've turned the wedge around, so the guy is sliding out. So the friction acts opposite of the relative motion. Like that. And that's the lowering case, okay? To check self-locking for a wedge, you turn the P around, and you basically say, so if a wedge is stuck under a door, or if this is an axe head stuck into a log, then you have to apply a positive force to pull it out. And so that's this case. You have to pull on it with some P to get it out from under the door. And so that's why you draw this case of P, the pulling case. And what you're looking for is P has to be either 0 or positive. If P is 0, then that means the wedge is on the verge of popping out all by itself, without any application of P at all. But more typically, if it's really locked in there, like an axe head, then you really have to pull to get a positive P to get it out. Does that make sense to you? So to check self-locking, what you have to do is first of all draw this picture, which is the pulling case. And then there's two ways, once you've drawn this picture, there's two ways to check for self-locking. I'm not going to go through the notes here but in my notes, I actually give you a theta versus mu equation that you can derive. If you're looking for a good time this weekend, you can follow the notes and go through the derivation. But the point is, if there's a particular mu on this wedge, then for that particular mu, there's a particular theta at which P is exactly 0. So the wedge is on the verge of popping out. And so this equation, if you just plug in the mu that you're given, that'll calculate a theta, and then you compare that theta to the actual theta of your wedge. And if the theta of your actual wedge is larger than that theta, then it's not self-locking, it's just gonna pop out. If the theta of your wedge is less than this guy, then your wedge is gonna be locked. So you can use this equation. The other approach is to actually solve for P. And again, if P is exactly 0, then it's exactly on the verge of popping out. Or if P is positive, then if not popping out on its own, you have to pull it out. And so that's self-locking as well. So what does that look like on a test problem? So if you have a wedge problem, old exams. So these are old exams. So there's 2 different flavors of self-locking. So to test if a wedge is self-locking, one does the following. And so you apply the force P pulling on the wedge with P is exactly equal to 0. So that's basically the case where it just becomes, it's on the verge of self-locking, it's right on the limit. The P pushing don't apply. The P pulling with mu is 0.5 doesn't make any sense. So there's only one answer here that makes sense, and that's A. There's a better test here, which is this guy, which basically says apply force P pulling on the wedge, solve for P, and for self-locking, P must be greater than or equal to 0 to pull it out. And so this is a more complete answer, and that's C. All of the P pushing cases don't apply, and then the pulling with something weird doesn't work. So that's a common conceptual question on wedges, okay? There's single wedge problems and there's double wedge problems, but the double wedge problems are often too complicated for a test. And so if you look at these old questions, most of these involve a single wedge. And you're just drawing a free body diagram of the wedge and trying to solve for something that you need for. Often you're given the normal force to make the problem a little bit easier too. And maybe one side of the wedge is smooth and the other side, there's only friction on one side. Again, to make the problem a little simpler. But I put several practice problems here from old tests for you to look at. Questions on wedges. Finally, belt friction. Belt friction. I'm kind of zipping along here, but the notes will really help you if you look at the notes. So belt friction problems is basically where you have, this is not a V-belt, this is a flat belt or a rope that's wrapped around a tree branch or around a what's it called? What's it called? A capstan, capstan. And so sometimes in a railroad yard or a harbor, they'll got this chain or this rope from a car that you're trying to move, and you put a few wraps of rope around this capstan, and all you're doing is providing just enough tension to keep that rope locked onto the capstan, and then the capstan actually provides the torque necessary to move that heavy railroad car or whatever. And so the equation for a dry friction problem is basically this T2 is equal to T1 e to the mu beta. And so you basically have a belt coming around a fixed drum. And you got this guy here, and you got this guy here. So this is a weight. Motion is impending this way. Motion impending. This is T2. This is T1. T2 is usually the larger value in the direction that motion is impending. And the equation that we use is T2 is equal to T1 times e to the mu beta. And beta is the total angle that you see here. That's beta in radians. And you're typically given a mu here between this belt and that drum. It's not a function of the radius of the drum. And so this could be a small tree branch or it could be a large drum of some kind. It's just a function of mu and the angle. So you have to get the direction right. And so in this case, motion's impending upward. And so I'm applying a larger larger T2 to try to initiate movement upward. If I'm applying a very small force here, and my motion's really impending this way, then this guy becomes T2. So this if this W is 100 pounds, then that becomes your T2 if motion's impending this way, and then this becomes your T1 because it's a smaller value. And so you've done this. And so basically, if you've wrapped a rope around a tree to lift something or whatever, to prevent this guy from falling, you can just apply a small force to keep it locked in place. And that's where the motion's impending and falling. Conversely, if you try to raise this weight, then you have to apply a much larger force to get the motion to impend upward. One of the things students have trouble with is getting the angle right. For example, this problem here, you've got 3 different drums. And how do you get this beta 1? How do you get these betas here? And how do you get these betas here? I don't really have a good answer other than draw a big picture. Just a big enough picture so you can see what's going on. So if you start with this drum here, that picture right there. Is your gimbal still tracking? I guess it is. Have you looked at the battery? Is the battery okay?
I mean, the battery is at 66%, so.
Okay. So
we've been going for almost an hour now, so.
It hasn't overheated yet either.
Yeah.
We need to wrap up, but let's finish this. So to get the beta for this guy, draw the picture really large. As large as it takes for you to see what's going on. And this belt is coming off at 20 degrees. And this belt is coming off here at 70 degrees. If you actually take a piece of paper and lay this right here, and think about this radius and then this rope. And if I take this rope and drop it down 20 degrees from here to here, then this line rotates 20 degrees. And so that becomes 20 degrees there. And basically the same thing happens here. If I start out with my rope here, and I rotate this through 70 degrees, so it goes from here down to 70. And then this angle becomes 70 degrees. Does that make sense? And that's a pretty full, just draw the picture large enough so you can see what's going on. And so now the total angle here is 90 degrees. So our theta is 90 degrees. So our beta is in radians. So this is 90 degrees over 180 times pi. And so it's basically pi over 2 is the beta for that drum there. And if you come to this guy, it's 70 here and 35, so it's 105 degrees times pi over 180. And then this guy here is 90 here plus 35, and so that's 125 total, and times pi over 180. Okay, and just draw the picture large enough to see what's going on. Does that make sense? So that's the belt friction equation, and you got to get the impending motion in the right direction. And I've given you some practice problems. If you go to your practice problems for belt friction, old exams. And so this is a force to initiate moment upward. And so this P is your T2. In this case, it's on the verge of moving down. This guy's on the verge of moving down, so this is your T2 here. If you got multiple posts like this, then the way the formula works, and if the mu is the same, then you basically don't have to deal with each post. And it's basically, if you get multiple posts, and you can work this math out. If you have multiple posts, then you can just basically sum all of your betas. And if you have the same mu for all the posts, then basically the T2 is equal to T1 times E to the mu times the sum of the betas. So you can add up all that. So you don't have to deal with each post separately. You just, again, if it's the same mu, then the beta here plus the beta here is the total beta times the single mu, and then you can calculate what you need. Okay. Well, I think we'll stop here tonight. This basically gets us through friction. We'll schedule another time to do centroids and pappus of Vildinus and composite areas for centroids. And then at that point, you've got more questions about anything we can, and by that time you should have looked at some of these guys so you can kind of see what's out there, and you might have questions on it. So we can address those questions. Centroids won't take as long as this stuff, and so I can circle back and answer any of your other questions if you want at that point, whenever we can schedule. I assume probably Sunday or Monday night or Tuesday night or sometime.
Probably next Monday.
Next Monday.
For us.
So, but just communicate. Monday would work for me, and we can do it. Questions? Anything? Has this been helpful?
Yes.
We're kind of flying. We're kind of covering all the ground here, but you talk to Josh about getting access to the drive, and that will help a lot. And then we'll just pick it up again Monday night.
Perfect.
Thank you all.
Thank you.
And hopefully we'll get these videos posted so then you can